Hey everybody, just a quick shout out here to Game Chops for the background music that they do retro games and they remix the game music, which is awesome, and they release it for free, so anybody can use it. Anyways, I love it. So let's show you. Earlier I did this. I wanted to continue with decor on my project. So what I did was I took the burden off the CPU and put it on the GPU, which makes it so much more efficient because now I can use the CPU for all kinds of other stuff like input and gameplay mechanics and stuff. Anyways, this is the result here. It's one of the quote-unquote asteroids spinning. It's not done yet, but so that's version 1. And if you look here, we have all these the Vertex shader. Let me show you quickly the Vertex shader for that one because updated ran to the Vertex shader because this is where everything happens in the Vertex shader for that particular one. So first we take the position that's sent in from the GPU, okay, and we're just doing quads and instancing here. So asteroid 1. At least it loaded, that's good. See, so elements, instance. Okay, so what's happening each time is these vertices are being referenced in this order by the indices given. Okay, and then the vertex shader is doing all of the transformations for this. So the new position is the position that's sent through the vertex shader. It's scaled locally, it's scaled, so you can scale it to whatever scale. Then the local and the world rotation setup are calculated right here. Okay, so the local rotation, which is LM, designated by LM, that's kind of important because I calculated both in this first version and I realized I used the same rotation for both, for the local rotation and the world rotation. So anyways, then we moved on to world translation. So that puts these asteroids into a grid of whatever grid I say. In this particular case, I hard-coded 6x6. And then we did the world rotation, okay, and then we set the position in the world. So in other words, like if it's off on the side there, and you'll see it in just a second. Of course, we just saw it. And then the aspect ratio is calculated right here at the very end. Okay, so that's all done in the Vertex shader, which is one way to do it. And it really gets a really, like I said, it just gets the burden off of the CPU. So the other way to do it, and there are other ways as well in addition to the ways that I'm doing it, but the other way to do it is to use the geometry shader, and let me show you that. So this one, let me run it first, and it looks very similar. I used a different texture. I was just kind of playing around. So what I took was this vertex shader and all these calculations, and this is the vertex shader for the one where I transfer everything to the geometry shader. So first we take the bounds, like in this case it's a 5v5, 5 by 5, and then we pass the texture into this, there's a structure that we're going to use up here. This is the out variable that goes from the vertex shader to the geometry shader. Okay, in addition to all the built-in variables and stuff. Okay, and it's got a texture coordinate, a vector 2 texture coordinate, a vector 2 bounds xy, which is the 5b5 in this case, and it's got one transformation, which is a matrix 2. Now the reason it has a transformation matrix is because the geometry shader is going to be operating inside of a loop, doing, like, let's say the 5b5, right? So that's going to do 25 different calculations. So it's better to do the calculation here in the vertex shader. So I do the rotation, then I figure out in advance the cosine and the sine, and then I put this cosine and sine inside the little matrix function, and then I pass that through as the world rotation. Now, in the geometry shader, okay, this comes through. Now, what the geometry shader does is it takes points, okay, and it outputs a triangle strip with a maximum output up to 170 vertices. That is the importance of what we're doing here in the geometry shader. Excuse me. So everything that the geometry shader has access to is the GLIN built-in variables, and then the GSIN, which we just sent from the Vertex shader. So this is in, but it's called VS out. So anyways, and then the only thing that goes out that we have to define is the VTEX, or the FTEX, which is the fragment shader texture coordinates. Okay, we'll get to this in a second. This is the function that I created. So one thing that I did was I took the hard code of the, instead of instance rendering, all we're doing with this particular class, okay, let me show you this really quick, okay. All we're doing, instead of the instance running, we don't need that. I know I have it in there, but that's because I didn't delete it. All we're doing is we're rendering one point. This is it. So we're rendering one point, and we're sending it through the Vertex shader, and then to the geometry shader. And then we've got 4 vector 4s in an array defined right here. These are the 4 points. Okay, and so instead of using elements rendering and referencing the indices, I've got, you see the indices are listed right here. So if you look at the last iteration of this, right, if you go back to, where was I at? This one, see, 0, 1, 3, 1, 2, 3. Those are the indices of the various triangles that reference this vertices set here. Well, now I've got that in the Vertex shader in this function that I created, Vertex 0, 1, 3, 1, 2, 3. Those are the 2 triangles in the quad that we're rendering. Whoops, this is the second triangle in the quad. I use copy paste to make all this, so there we go. So basically, what the geometry shader does is it takes the Vertex shader and it pulls it back and it says, we're going to use you a bunch of times. So what you do is you set up like you do for every single Vertex shader, and then you call emit vertex. And the state of the quote-unquote GPU at that time is what creates a vertex. Okay, so instead of calling GL position and FTEX equals that in the Vertex shader, I do it here within the algorithm for the geometry shader. And then once I call emit vertex, that vertex is created just as if I had done all the calculations and everything up to this point inside the Vertex shader. However, we're still operating inside the geometry shader. Okay, wrap your mind around that for just a second. So in addition to that, what I'm doing with the position is I'm calling a function called create asteroid grid. Okay, so each time this function operates, I send it the vertices, which I defined up here, and I'm sending it just the XY because we're not using the Z and we're not using the W, so we're just using the XY. And I've hidden the texture coordinates inside of the remainder of the Vertex 4. So we're just sending in the XY to the function, and then the texture coordinates are being sent on through ZW into the FTEX variable, which gets sent out to the fragment shader, which is the next step in the OpenGL pipeline shader stage. Okay, so now on to this create asteroid grid. So those coordinates are sent in, right? And then does this stuff look familiar? Well, the comments are exactly the same as the fragment shader from the previous version. So what I did was I just moved everything over. New position equals in XY. So those coordinates that are sent in, the scale, the new position is scaled right here, so it's the local coordinates of the, and it kind of translates up to 3D coordinates. This is how 2D coordinates are transformed into the asteroid version that I did, and ultimately 3D coordinates are transformed from coordinates inside your head with the local model coordinates to world coordinates where you can put the model anywhere in the world. So what happens first is the scale, and then we get the rotation, okay? So that rotates the model any way we want. And then the world translation takes that model, and in this case, it's each one of the grid points, so 5 by 5. So every single position within that 5 by 5 grid is calculated right here as a world translation. It's a little bit easier calculation because instead of figuring out mathematically where we're at, we're using a loop inside the geometry shader. So I goes from that variable that we passed in, which is 5, and this variable that we passed in, which is also 5. So I guess we could do a rectangle and do an odd number, but in this case they're square and they're both equal. But anyways, so there the bounds are calculated. This is the offset, so we have to start at negative the maximum of the boundary divided by 2. Okay, so that'll give us the center. Whoops, that's kind of cool. I didn't realize Visual Studio Code did that. Times the scale, okay, and then times, you know, each one of the things has a spot in the thing. Okay, so that's the world translation. I'm sure I explained that correctly. And then we get world offset equals world offset times this world rotation, which is actually the same rotation. Initially I thought there was a negative involved somewhere. You might see that in my stream, but that's not correct. They both use the same rotation. It's just a matter of order in which the rotation occurs. And the new position plus equals the new position plus the world offset, which puts it into the grid, the 5 by 5 grid, and rotates it everything, and then we get the aspect ratio applied, and then it makes it a smooth transition. If you saw my streams, you probably saw a little bit of a distortion, warping I called it, and it made you kind of dizzy. So wouldn't look at that for too long. But anyways, so again, the end result here. Let's get a screenshot. Wait, let's get a good screenshot. There we go. That's the screenshot. That's the end result. And hey everybody, thanks for watching. If you'll notice in the link in the description, there's a new Ko-fi way to support me. You can support me by either buying all the screenshots for $5 or more, which is 645 images of all the screenshots I've ever taken from working with OpenGL for the 5 years learning. And then I've also got all the source code for this stuff so that you can actually start to work with OpenGL. You can actually build a skeleton for a game engine. So basically with OpenGL, you don't use Godot, you don't use Unreal, you don't use Unity, you don't use GameMaker, you don't use any engine whatsoever. Every single time you make a game, you build an engine for that game. However, you can also learn how to do that and save your status and save what's called classes, and you can instantiate an instance of your game and then customize it based on what you want to do. I haven't gotten to that point yet, but we're slowly getting there, and I take lots of tangents and lots of eye candy distractions along the way. So anyways, if you want to join me on this, you can buy all the source code. It's over a 240 megabyte download. It's available for $20 or more donation at Ko-fi. Again, you'll see the link in the description, and thanks everybody so much for watching, and thanks for liking, subscribing, following, and checking me out on Twitch when I'm over there, checking me out on YouTube, streaming, which I like to do usually early in the morning, like between 6 in the morning Pacific time and noon or 1 Pacific time. So all right, thanks everybody, and I appreciate everybody who watches. They're really great to have you in the chat and come and say hi. Really great. Thanks so much.